leave a trail of destruction. With collapsed buildings comes the tragic loss of many lives. Today, designing and constructing to withstand earthquakes has never been more important. Ironically, the solutions may lie within the ruins. Once the rescue teams leave, it's the turn of the global network of earthquake engineers. They come to try and unlock the buried puzzles in each disaster. They're looking for the clues that may someday lead them to their ultimate goal: the earthquake-proof building. Earthquakes may cause devastation, but across the world, engineers are striving to combat their worst effects. There are solutions for buildings.
So when the earthquake strikes, everything below this elevation will go in whichever direction the ground moves.
There are solutions for industries.
They run 24 hours a day, 7 days a week. They want to be up and running right after an earthquake.
But above all, there are solutions to protect life.
It doesn't matter what the numbers are. One person getting hurt is too much.
This is a simulated earthquake. It's good, but not good enough, because earthquake engineers the world over know that designing a safe building means studying real earthquakes.
The only way we're going to find out whether we have it right is to have full-scale tests, and that means having earthquakes.
Earthquake engineering is actually a learning process. You know by experiencing new events, new damages.
Unfortunately, earthquakes and Mother Nature at this point is probably the best sort of test bed. We do a lot of tests in laboratories to see how buildings and many things perform, but it isn't until you get out into the field and you actually have a major earthquake that you really discern what has worked and what has not worked.
In August 1999, an earthquake struck the densely populated Marmara region of Turkey. With a magnitude of 7.4 on the Richter scale, 20,000 buildings were destroyed in just 45 seconds, and 17,000 people would lose their lives. Trying to conduct research in this sort of situation isn't like any other engineering job. It can be a harrowing task.
When we got to Turkey, probably from my own personal perspective, what was very disturbing was that there were still many buildings that were still damaged, and knowing that there were still many people that were in these buildings was something that was very hard to take.
The first thing engineers must do is carry out post-mortems on the damage. But entering the aftermath of an earthquake can be like arriving in a war zone. Devastated neighborhoods are no longer recognizable, and the earthquake engineers can't always work out where they are. In the Turkey earthquake, Ron and his colleagues had to use global positioning and satellite maps to help them pinpoint specific collapses that needed investigation.
One of the problems that you will find when you go to earthquake-affected areas is that the area of the city is just not the same as what it was before. A lot of times it's very difficult to recognize streets that had names, that had buildings there, and so it is almost absolutely necessary that you utilize new technologies.
But it doesn't take high-tech tools for engineers to know that a building made of cheap materials can disintegrate in seconds, no matter how well designed. And 9 out of 10 people living in seismically active areas belong to developing countries. Often, there simply isn't the money to spare for high-quality materials like steel reinforcement. But successive earthquakes have shown that unreinforced concrete is the worst sort of material to withstand an earthquake. In high-rise buildings, it'll cause columns and beams to fail and stories to collapse on one another in a phenomenon known as pancaking. However simple or complex the failure, there remains the puzzle of why one side of a street is a write-off, while the other has hardly a scratch. Earthquake engineers know that to understand what happens to buildings, they must start with the ground beneath their feet. Earthquakes travel through the ground in the form of P, primary, and S, secondary waves. S waves are the more violent and are what cause the damage to buildings. The type of ground through which they travel will amplify or decrease their intensity. The softer the soil, the greater the shaking. And just like sound and light waves, seismic waves can be reflected and focused. This can make damage in some neighborhoods worse and in some instances unpredictable. If a building straddles a fault, it may literally be ripped apart. And in certain kinds of soil, it may sink into apparently solid earth because of a dangerous and dramatic process called liquefaction. That's what happened to the lower stories of these Turkish apartment blocks. This extraordinary footage is the only time that liquefaction has ever been caught on film, and was taken during the 1963 Niigata earthquake in Japan. This is water actually pouring up from the earth during shaking. This process has tilted buildings and caused them to sink in many different earthquakes. The most dramatic example of it ever witnessed in the United States took place in San Francisco's Marina District during the 1989 Loma Prieta earthquake. Science teacher Ken Finn was leaving work when he found himself literally riding the surface waves of soil liquefaction in a car park.
It was a little bit after 5 o'clock, and I was in my car getting ready to go home when the car started to move up and down as though someone were jumping on the bumper. I realized we were having an earthquake, and the ground was moving so much it was hard to walk. I had to kind of be careful as I moved around. The parking lot was moving in waves, maybe 3 feet from the top to the bottom, and it was maybe in like square regions, about 6 feet by 6 feet. And there were just these hills and valleys that would appear and reappear, almost like a standing wave, and that was throughout the parking lot.
In the ground beneath Ken's feet, the earth was soft and had a high water content close to the surface. When the shaking started, the loosely packed solid earth particles separated from the surrounding liquid. Then, as the heavier particles sank, water rose to the top, turning the ground to wet jelly. Driving enormous piles deep into the ground is a solution where earthquake engineers have identified liquefaction-prone areas. But there are reasons other than soil conditions or poor materials for buildings to collapse. Earthquake engineers dream of catching an earthquake, of recording enough information to know exactly what happens to different types of buildings during violent shaking. In September 1999, a second massive earthquake hit the heavily populated island of Taiwan. It was the most instrumented earthquake in history and was caught in the memories of thousands of computers all over the country. The information it gave earthquake engineers took them a step closer to understanding key reasons why buildings collapse. Taiwan is one of the most seismically active pieces of land in the world, sitting on the Earth's surface where the seabed of the Pacific Ocean pushes towards the mainland of Asia. When these forces were unleashed, the heavily industrialized island was thrown into chaos. Before the earthquake, the bustling little market town of Puli was an attractive and popular tourist destination in the center of the country. Unfortunately, all that was about to change. Mrs. Chu lived with her husband and son in a small apartment in the center of Puli. On the day before the earthquake, she was happily going about her business. Everything was normal, except for one thing.
Before the earthquake, the fish were jumping around in our fish tank. Suddenly, they began to strike the glass. Some were bleeding, and some even knocked themselves out. We just thought that the fish were being foolish and did not realize that a catastrophe was about to happen.
At 2 a.m. on the 19th of September 1999, an earthquake measuring 7.6 on the Richter scale hit Taiwan. The epicenter was a village called Chi-Chi. Puli, dangerously close, sustained massive damage.
That night at about 2 o'clock, the room began shaking up and down and from left to right. We heard noises. It was the glass smashing. Ping, ping, pang, pang. The noise was so loud. The glass smashed. Bang, 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 bang. A really violent sound. Gas tanks fell down. The glass exploded. Furniture fell down. The sound was very, very loud. My husband went to my child's bedroom to wake him up. When I came out of my flat, we saw our neighbours who had come down from the floors above. We moved one by one. I had a flashlight in my hand as there was no electricity. When we came down the stairs, we arrived in the courtyard and found the security room, which was the only exit out of the building, had completely collapsed.
Others didn't have such a lucky escape and needed urgent medical treatment. But in Puli, they were about to discover that one of the main hospitals had collapsed. Earthquake engineers are always learning from the terrible experiences of real events. In the Taiwan earthquake, a brutal lesson was learned by one hospital. Hospitals are what earthquake engineers label critical facilities. They must remain standing and operational in an earthquake. But in Puli, the hospital had become one of the casualties, leaving only the car park as the operating theatre.
The patients had to be evacuated. Those that could not walk, we had to carry on our backs down from the third floor and put in the square in front of the hospital.
All the hospital's medical supplies had been trapped under the rubble, and there was no electricity or water. Doctors were forced to do operations in darkness with only basic supplies. Many victims died as a result. A 100 miles north in Taipei, Chi Feng Soon was asleep in his 12th floor apartment when the massive earthquake hit. The building collapsed in seconds, one of the few seriously damaged this far from the epicenter. For Chi Feng, it was the beginning of a nearly fatal ordeal.
We felt the house start to shake, but we thought that it might not be anything too serious and it might stop after a while. However, it became stronger and stronger. We were nervous and got up to try to escape. I opened the door and tried to get out, but it was too late. Everything above me fell down like the earth had cracked and the sky exploded. But I couldn't see anything. So if you can imagine riding a spaceship, closing your eyes and suddenly dropping to the earth, it was that sort of feeling.
In the space of a few seconds, the entire building collapsed. Over 60 people lost their lives, including several of Chi Feng's family members. Incredibly, despite dropping 12 floors and having several upper floors collapse on top of them, Chi Feng and his younger brother were still alive. But they were trapped together in a tiny space, virtually unable to move. The boys talked to comfort each other in the darkness.
A couple of days later, we were talking when I looked at my watch and realized it was my birthday. My brother said to me, "Shifeng, I never give you anything on your birthday, and I have nothing to give you now, but I give you my favorite necklace as your present." He then took off his necklace and put it around my neck. I was so moved.
Chi Feng and his brother lay buried in the rubble for days, surviving only on rotting fruit and dripping water. At night, they could hear the voices of rescuers, but no one, it seemed, could hear their desperate cries. By the 6th day, Chi Feng and his brother had all but given up. Starving and delirious, they resigned themselves to death. But incredibly, digging in the rubble, Chi Feng's younger brother managed to find a tiny hole and escaped to alert the rescue teams to his brother's situation. Amazingly, both boys recovered physically from the experience, but the building collapse is something that they can never forget.
The fear is always there, and we will never forget that experience. I remember during the first month after the earthquake, my brother and I found it difficult to sleep. We would go to bed and lie staring at the ceiling because we thought that it might fall down again. All we wanted to do was find a place to hide.
Back in Puli, the aftermath of the earthquake was terrible, even for those who had escaped. For weeks, nothing functioned.
I thought that Puli had been completely destroyed. I just wanted to cry when I saw that the buildings had collapsed and so many people had died. Every time when I came to collect my belongings, I cried. I thought about all of the families and what they had built up through their whole lives, and all this had gone just because of one earthquake.
With the rescue operations over, it was time for the earthquake engineers to see what could be learned from the tragedy, and patterns were starting to emerge. Professor Tsai from the National Earthquake Engineering Center in Taipei has come to Puli to look at how residents are learning from the past and building for the future. He's starting his investigation at the hospital and reveals why it didn't stay intact, while other buildings around it had weathered the quake with barely a scratch.
I think, first of all, the shaking was very severe, okay? And then secondly, it's unlike those shorter buildings nearby. This building is slightly taller. And in addition to that, this building has more open spaces.
Hospitals need more open spaces for wards and operating theatres, but in an earthquake, open spaces can be a building's worst enemy. It means there are fewer walls to stiffen the structure.
Relatively speaking, this building is weaker and softer. That's why this building was so severely damaged during the earthquake.
So the hospital engineers are now surrounding columns with steel jackets and installing reinforcing bars to increase strength. Modifying a building after it's built is called a retrofit.
They are retrofitting this building rather well, so I think the building is much stronger now.
Elsewhere in Puli, Professor Tsai sees positive steps being taken to try to prevent the same sort of damage from occurring again.
In old times, because it's difficult to afford good materials, so people use simple reinforced concrete and bricks to build their buildings. Now, after the Chichi earthquake, because the severe damage observed during the earthquake, people now is willing to pay a little bit more, not too much more, to buy steel column and steel beam for their buildings now.
Fractured columns and beams and poor reinforcement are common to many earthquakes. But the open spaces that had weakened the hospital are common in traditional Taiwanese buildings, causing a widespread dramatic form of collapse. It was a phenomenon called soft story failure, and it grabbed the attention of engineers from around the world. This remarkable form of failure causes, as seen here, the complete flattening of the ground floor into a space mere inches high, while the upper floors can have hardly a window broken. But how does this happen? Professor Tsai explains.
For example, this building doesn't have walls in the direction parallel to the street direction, so it makes the building relatively weak and soft during the earthquake. Especially if you have typical floors above the ground floor, you have regular partitions, regular walls in every direction. It makes the building, irregular on the ground floor. And if we have a shaking in this direction, the building can easily fall down in this direction.
In addition to soft story collapses, another pattern emerged. Its most striking feature was the height of the buildings, which sustained most damage. The majority were between 8 and 12 stories. This was because the frequency of the earthquake was in tune with that of the buildings. Engineers call this resonance, and later we'll see some radical solutions to this problem. The new knowledge learned in Taiwan and other earthquakes has helped engineers predict how all sorts of buildings will behave, and crucially, how they can design them to protect lives. Although life goes on as normal, Californians live in the constant shadow of a big earthquake. These children, in a Los Angeles school, are practicing their earthquake drill. But even though Californians know that an earthquake is inevitable, they don't always prepare for it. As a professor of architecture at the University of California at Berkeley, Mary Camario has spent many years researching the attitudes of Californians towards the big one. What she has found is not good news.
People in California are marvelously oblivious to the reality of earthquakes. Even though we live with this threat on a daily basis, there's a 70% chance that there will be a major earthquake somewhere in the Bay Area in the next 30 years. And somehow that probabilistic risk doesn't translate into people's everyday lives. In people's everyday lives, they're worried about whether they're going to pick up their kids on time from school, whether they're going to get this work project done, whether they're going to meet a deadline. And so they tend to take care of immediate problems as opposed to preparing for some future problem.
The evidence from events like Turkey or Taiwan has helped to develop amazing new software technology that can predict loss. An ordinary laptop computer can confront a property owner with what would happen if their building was hit by an earthquake. Steve Shakerlian is an earthquake engineer in California. In his work, he can use this technology to predict earthquake effects at any address in America, like this one, for example, a typical Californian building.
Today we have the technology and the capabilities of determining what levels of damage we expect in buildings. And there's many computer programs that are out today that do this, where you can basically input the data of where the building is located, what type of construction it is, the vintage of the building. For example, we can run this particular building here so we can identify it relative to where the hazards are. So what we do is we input the data and we find out the location of the building, and it's located it. Now what we do is we put in the various different structural attributes. And then we'll save that data. And then what we do is we'll put in what the earthquake hazard is. So what we do is now we'll load the database of all the faults for a 500-year return period. And from that hazard, it does hundreds of thousands of simulations where you can then identify what the actual potential losses are for a given earthquake for this particular type of construction. It also provides you the percent of damage and the dollar loss associated with it for different various confidence levels.
But knowing what the damage might be isn't the same thing as doing something about it. Many people in high-risk areas choose to do nothing about quake proofing, leaving their families in potential danger from an eventual, inevitable earthquake. The most dramatic collapses in earthquakes may be multi-story apartment blocks or elevated freeways. But in fact, the biggest group of damaged structures in a Californian quake is something much more down to earth: single-family wood frame homes. Here in Los Angeles, the city is trying to find a way to encourage its citizens to prepare themselves for a future earthquake. For the first time ever, the city is testing a scheme to grade homes according to their state of preparedness. The better protected, the better the rating. Getting a poor mark could mean not being able to sell your home. Getting a good one could mean saving your family's life. Shafat Kazi is a structural engineer carrying out an assessment on a traditional Californian home.
What we're going to be looking here is for the cripple walls. The cripple wall is actually the portion between the foundation and the floor joist. This 18 inches portion of the house typically carries the earthquake forces from the foundation to the house. And in a large earthquake, the foundation moves, and if the forces are transferred, we get like a scissor effect where the cripple wall actually fails and the house actually slides out. Going to the crawl space, it's kind of important to look for the anchorage between the mud sill and the concrete foundation, and we typically look for whether the house has actual bolts. Some of the older houses did not have bolts, and as you can see in here, there is a bolt between the foundation and the mud sill, and that does help this house to perform better in an earthquake.
But all too often, Shafat finds that there are areas that could do with improvement.
As you can see, they have a typical concrete pier with a post sitting on top of that, supporting all the interior floor joist. That typically is not good for a house. A continuous footing would have been the best, but because it has a pier. But one good news they have is these cross bracings that keep it in position during shaking.
Most Californians' homes could be saved simply for little cost. But not all buildings are so easy to protect. Steve Shakurlian, an earthquake engineer, works with major companies in Los Angeles. In January 1994, he'd just completed a project for one of his clients, a brewery, who were gearing up for the Super Bowl, their busiest time of year. Just as footballers protect themselves from the impact to come, Steve had to protect the Northridge Brewery against the worst of nature's fury. What he didn't realize was that his skills were to be tested in a matter of weeks. And with the biggest football game of the year just around the corner, damage could mean losing millions. Steve and his team surveyed the factory and decided upon some crucial changes. The main building was the first to be reinforced.
This is a 1950s vintage concrete shear wall structure, and the earthquake forces are resisted by the walls you see back here. And when we first did an analysis of the structure, many of these walls had openings in them for windows and ventilation, things of that nature. And so what we did is in our analysis determined that in some of these instances we would have to close up the openings. And as you can see right here, this one solid section of wall right here, there used to be a window similar to the two over there on the left-hand side, right in there, and what we did is we infilled that so that you had more of a solid wall where the loads can go down through the wall much more evenly.
Bracing was the next weapon in Steve's arsenal. From basic foundations to high-tech equipment, this simple form of strengthening seriously improves the chances of resisting earthquake forces. But Steve also had another technique up his sleeve.
And this is what they call a seismic separation. What happens is when you have two buildings that are in close proximity to each other, during the earthquake they'll vibrate, and they don't always vibrate in exactly the same phase. Sometimes what they'll do is they'll go towards each other or they'll go away from each other. And what this space does is it allows the building to move without pounding against the adjacent building and cause damage to the structures.
Steve's handiwork was to be tested within weeks when the biggest earthquake to hit the area in 30 years struck in the middle of the night. All over Northridge, buildings were shaken violently. Around the brewery, those who experienced the shaking were terrified.
I was asleep, it's about 4:30 in the morning, and I heard that first shake, and instead of being kind of a delicate shake that was going to build into something, it just launched into full sound and fury right away. So I jumped out of bed, grabbed the door frame, and as I was holding onto the door frame, I was listening, and I could hear things falling over. I could see the floor moving in the corridor. I could hear glass breaking. I looked up, and the light in my bedroom exploded, and then all the power went out.
It didn't look good for the brewery. Steve rushed to Northridge, but his first thoughts were with his family.
My son and I, we immediately got into my car because of my parents live right in Granada Hills, very close to the epicenter. And I wanted to get up there as soon as possible to see how they were.
Steve's family had been lucky and escaped unscathed. But elsewhere in the neighborhood, the damage was enormous. And as an on-call earthquake engineer, Steve knew he would have plenty of work to do as a result.
I called the office where they had set up basically it's almost like a war room what they do. They basically set up a phone system with people, and then what they do is they coordinate engineers going out to the different locations, whether to our clients to help them assist where they have earthquake damage to their buildings, or whether it is to go out and collect data to do reconnaissance.
Arriving at the factory, Steve discovered that the brewery had sustained virtually no structural damage, and the company saved millions of dollars in lost revenue. The Super Bowl watchers got their beer. It was a highly successful project, but Steve had learned that being an earthquake engineer was more than just a job.
When you actually see it in your own backyard, and it's people that you know, it's buildings that you have designed, it really hits home, and it hits you more closely because you feel like you're part of it, and you wanted to make sure that nobody got hurt in any of the buildings that you designed.
Established techniques have been very successful for conventional businesses, but the billion-dollar industries of the 21st century demand new solutions. Here, price is no object, and earthquake engineers can apply their ultimate state-of-the-art technologies. From Seattle to San Diego, Taipei to Tokyo, many of the world's high-tech economies lie in earthquake zones. These industries demand the highest possible levels of seismic protection. In the 1999 earthquake in Taiwan, the high-tech Hsinchu area, Taiwan's Silicon Valley, was seriously affected. The companies here supply a third of the world's computer chips, and disruption could have global implications. When the earthquake hit, the country was plunged into darkness when power lines ruptured. For the silicon foundries, loss of power meant loss of production. After 2 days of lost production, totaling millions of dollars, the Taiwanese government made the unprecedented decision to divert what little power remained from the rest of the island. But power supplies are not the chip plant's only worries. These factories have many different expensive elements that need protecting. John Dyson is the earthquake engineer responsible for the seismic performance of one of the biggest factories.
This goes beyond life safety, but a lot of this facility, I mean, they run 24 hours a day, 7 days a week, and production and business interruption is certainly one important factor. They want to be essentially up and running right after an earthquake.
But for a seismic engineer, a silicon chip plant is a real challenge. Pipes carry toxic and highly corrosive gases and must have emergency shut-off valves linked to seismographs. To avert complete disaster, they stop the supply at the first hint of the smallest shake. And although the familiar bracing is needed to protect the building itself, when the building's contents are crucially important, they must be seismically protected too.
They're a lot more expensive in terms of the overall assets of the building. They account for a majority of the assets in a fabrication manufacturing plant.
In the clean room, the area where the chips are actually produced, a single speck of dust can cause serious disruption, and earthquake protection is to a much more exacting standard.
In the clean room, we design a lot of anchoring system for expensive tools such that to prevent them from sliding or overturning during an earthquake.
But if the contents of silicon chip plants are expensive, the contents of the world's research laboratories may be beyond price. The University of California at Berkeley lies right on top of the Hayward Fault. A recent seismic survey set alarm bells ringing when they discovered the vulnerability of their most valuable asset, vital new research.
One of the surprising findings in our study of the Berkeley campus was how highly concentrated our funded research is. About 50% of all the funded research is concentrated in 7 buildings.
Like the silicon plants in Taiwan, Berkeley is a 24/7 operation, and the equipment carries a fabulous price tag. But if an earthquake hits here, the knowledge lost may be beyond price.
And we really cannot afford, as a major research institution, to allow those buildings to be closed. We can't stop for 2 years. The cure for cancer may be lost if a refrigerator tips over with samples in it.
This is a new challenge for the earthquake engineers of the future and goes beyond the demands of the past, making sure that an earthquake causes virtually no damage to a building.
So our goals have to be to figure out ways to continue to operate and never shut the campus.
The solution for Berkeley may lie in the untested new techniques at the cutting edge of earthquake engineering. In the new millennium, earthquake engineers are moving ever closer to their ultimate goal, the earthquake-proof building. If you need your building to stand up in almost any earthquake, there are some pretty amazing solutions on the market, and some spectacular ones on the horizon. Base isolation is a technique that literally separates a building from the ground beneath it. In a big earthquake, the ground will shake, but the building shouldn't. This technique is for big customers only. Los Angeles City Hall is the tallest building in the world ever to be base isolated. As an old building, it was an incredible challenge to earthquake engineers.
The more traditional way of installing isolation systems are to build it from the ground up. But because Los Angeles City Hall has initially been built in 1928, we've got the logistical problem of trying to install the isolators with a building in position and try and minimize damage to the existing building.
When an earthquake hits, City Hall will now be able to move 4 feet in any horizontal direction. In order for this to be possible, a 4-foot wide moat was excavated around the entire building.
We have to leave room for the building to occupy a zone once the ground has moved away. Because if you can picture the building standing vertically and the ground snapping away, the building remains in one position, the building has to occupy space, which means that we need a 4-foot wide zone all the way around City Hall.
The next thing that had to be done was to separate the building from its existing foundations. To do this, the engineers had to excavate down below the existing basement and place jacks under existing columns to keep the building erect. Next, 578 individual isolators were placed between the existing foundations and the new sub-basement, and the jacks removed to let the building rest on the isolators. Each isolator consists of alternate layers of bonded rubber and steel encased in a fireproof shell. When the shaking starts, the bottom of the isolator moves with the ground, but deforms to allow the building to stay almost stock still. For Richard's team, it's been a great achievement.
So I'm going down from the basement now down to the sub-basement, where all the isolators are. Down in this sub-basement zone, the head height is approximately 4 to 5 feet. And this is a plane of isolation of the entire building. So when the earthquake strikes, everything below this elevation will go in whichever direction the ground moves. After the event is complete, when the foundations come back to its original state, the building moves towards the bottom of the isolator and it will eventually reach an equilibrium point at rest. And all this occurs in a matter of microseconds.
Another cutting-edge technology beginning to make its mark in buildings is dampers. Damping technology started in military applications about 20 years ago. It was designed to keep intercontinental missile silos operational despite the effects of a near hit. Seismic engineers now use dampers to absorb the vibrations that would otherwise shake a building in an earthquake. Dampers are basically shock absorbers. These sort of dampers work by moving fluid from one end of the damper to the other through a small hole. Because of the force required to squeeze it through, the fluid becomes hot and the energy is transferred from movement into heat. When installed throughout a building, they damp resonance, reducing shaking. But if the molecules of fluid inside a damper could change their characteristics at command, engineers could make one part of a building stiff while leaving others flexible, allowing the building to respond to the earthquake in the best way possible. This is the realm of smart materials.
Smart materials for earthquake engineering applications are those materials whose properties can be changed in near real time.
Engineers have already identified materials that can be changed in mere milliseconds by applying an external force.
One example is the fluid contained in this syringe. We see that as we stroke the syringes backwards and forwards, we move fluid from one chamber to the next chamber. We now impose a magnetic field on this device, and we see that the properties of the fluid have substantially changed. And this offers earthquake engineers some unique opportunities in the years ahead as we look to improve how we control the response of structures.
The key to that control may lie in powerful computers. Together with smart materials, they could mean the advent of the truly intelligent building. As we'll see later, the computer would also allow engineers to contemplate other, apparently outrageous solutions. Seismic engineering has advanced at an extraordinary rate over the last 20 years. That, with the knowledge gleaned from recent earthquakes and advances in computing, engineers are getting closer to designing a building that really is earthquake resistant. Dr. George Lee is a leading authority on the seismic engineering of the future, a technology known as active control. He spent much of his career in biotechnology, applying engineering principles to the human body. Now he wants buildings to learn from us. Above all, it is the human ability to balance itself that generates his admiration. Humans balance themselves by their muscle system. Our brains and muscles work closely together to control our balance to an extraordinary degree. This is something that Dr. Lee sees around him every time he gets on the train to work.
We, of course, can see, can hear, can sense. So get the sensors, get the information to the brain, and the control tells the different muscles to act at a different tension level. Some totally relaxed, some fully tensioned. Some, for example, you want to bend the knee, that means you wanted to add some damping to that, minimize the impact.
These controlled movements made by Tai Chi enthusiasts may look simple, but they are in fact a great feat of human engineering.
Now if I'm riding on a subway car such as these, I feel motions left and right. That is the inertial force, weight times the acceleration in the horizontal direction, want to throw my body off. So I must balance that horizontal force by adjusting the three parameters, the weight and the damping and the stiffness.
Dr. Lee is working on a revolutionary prototype where this same system is applied to buildings. Just as our nerves send information to our brains, sensors placed around a building would feed into a computer. The computer would be linked to hydraulics and weights that would be the equivalent of our tendons and muscles. The technology is known as active control, and it enables buildings to respond to earthquakes in real time. In buildings across Japan and Taiwan, the first generation of this latest technology is being installed. A system known as tuned mass dampers is at the cutting edge of active control. During an earthquake, sensors throughout the building will send information to a central computer. This will activate a system of hydraulics that moves a counterweight, a huge block of metal, along a system of tracks. The engineers believe this should counteract the effects of resonance when the next quake strikes. The tallest building in the world is being built in Taipei, one of the world's most seismically active cities. The skyscraper combines the very best of conventional and cutting-edge seismic engineering. It'll be supported by the biggest super columns in any building in the world and will have a skeleton of dense steel reinforcing. But 88 floors above the ground, it will also have tuned mass dampers. No one knows how it will perform until the first earthquake hits. Unfortunately, advanced technologies are incredibly expensive and will remain the preserve of a few. Most people affected by earthquakes may never be able to afford such high-tech inventions. Across the world, though, engineers dream of something for everyone.
If you asked most earthquake engineers what they would wish, is that the technology and the design conditions that we know about, that they're actually implemented for all structures in an urban environment.
We sometimes have to think far ahead of time that we want to do something properly so that our children will not suffer from major earthquakes in the future.
But for all of them, their mission remains the same.
We're supposed to protect the public. When a public goes into a building that we've designed, they should feel safe and secure that the building is designed right and it's not going to fall down on them. As time goes on, we will improve and eventually we will find a building that will be earthquake resistant.